Hey everyone, welcome to day 20 of Math 133. And yeah, we only have 10 more days. Today we're going to talk about the Chapter 9 project. Um, Most of our projects are in Google Sheets. This one are Google Docs. This one is actually in the course pack. So it's on page 569, 569. So you're going to want to get that out. And there's 5 pages. Most of our worksheets have been 4, so make sure you grab all 5. Okay. All right. Um, so in addition to page 569, there's 2 other things that we're going to need. One is if you click on the Chapter 9 project, there is a link for random confidence levels. When you click on that, it's going to bring you here to StatCrunch. I will drop this in the chat for you because we're going to need that. Okay. So once you're in StatCrunch, make sure you sign in or register. Okay. The other thing we're going to need is we're going to need our data from our candy. It's okay if you already ate your candy. We don't need the candy itself. We just need the numbers. So the data and graphs one, which is right here for me. So I mentioned make sure you know where you saved that, right? Because we're going to need these numbers today. Okay. All right. So, now that I've got that, let's go to page 569. Chapter 9, Project Candy with Confidence. We are going to be building confidence intervals using uh, candy, our candy data. Okay. All right. So, answer the questions in the boxes. Scan and upload it into Canvas. 4 decimal places for z alpha over 2. All right. Um, so what we're going to be doing is we are going to be looking at building confidence intervals. A confidence interval is going to tell you what range to expect your population statistic to be in, your population parameter. So, in other words, so let's say I want to measure what percent of M&Ms are red. Well, I can't actually measure that because in order to measure that, I would have to look at my entire population. I'd have to open up every single bag of M&Ms and count them. I can't do that. Okay. Um, so instead, we take a sample and then we can look at, okay, what percent of M&Ms are red in our sample, and our sample percent is going to be close to the population percent. It's not going to be the same because I'm doing a random sample. So I might randomly get more reds or less reds than normal, okay? But I'm going to get close to the population proportion. How close? That's what a confidence interval is telling you. It's telling you how close to expect it to be, okay? Now, the confidence interval is going to need a confidence level, which is going to be another percent. Okay, we got percents flying all over the place, but this percent is going to tell you how confident you are. So we want to be 100% confident, right? We can never be 100% confident because in order to be 100% confident, we have to sample the entire population. We already said we can't do that. Okay. But we can be 99%, we can be 95. 95% is a normal confidence level. If you don't know what confidence level to pick, 95 is what you should pick, okay? Because we had said that a probability less than 5% is unusual. So opposite of 5% would be 95%. So we're looking at all the usual results with a 95%, okay? But you could be more accurate. You can look at 99%. You can be less accurate. You can be 90%. That's going to make it so you don't have to get such a big sample size, okay? But I mean, we know that 3 standard deviations is 99.7, so you can be really accurate, even with a reasonable sample size. So anyway, so we're going to select 3 confidence levels, and it says to use the StatCrunch file that I dropped in the chat to generate 3 different random confidence levels for this project. Now, that is not what you normally do. You don't just say, I don't know, pick a random number, okay? Normally, when you are building a confidence interval, it's important to have a conversation with your boss or your CEO or whoever it is you're building this data for, and ask, like, how confident do we need to be in these numbers? Okay. And if their answer is, oh, well, we need to be 100% confident, well, that means they don't understand statistics. If we can never be 100% confident, but we can, if they want to be 99% or 95%, those are normal confidence levels. Okay. So anyway, for our case today, we'll just pick some random numbers, I guess. So what you're going to do is you're going to go data, sample, choose confidence levels, and a sample size of 3. Okay, I just need 3 numbers here. Okay, so here's what you're going to do. So we're going to go to that StatCrunch file that I dropped in the chat. Okay, this random confidence levels. And these confidence levels here are, they go from 70.3% up to 99.8%. So there's not 100% here. We already talked about that. You can't do that. But 99.7 is 3 standard deviations, so 99.8 is a little bit better. You could, and we could have even gone to 99.9, 99.99. Okay. Um, anyway, so 95, that's a normal one right there. 95.3, 95.4.8, those are fine. Um, so we are going to have StatCrunch pick 3 of these at random for us. Okay, so you don't need to pick them yourself. So what you're going to do is you're going to do sample, data sample. You're going to select the confidence levels and then put in a sample size of 3. Okay. And basically what that's doing is just picking 3 of these numbers at random. Okay, and we hit compute, and it's going to pick 3 of those numbers. And you're going to write those down on your paper. So I've got 86.8, I've got 75.8, and I got 70.8. Okay. So your numbers will be different from mine. Okay. And that's good. The projects give you a chance to work with your own data, right? Your numbers for the M&Ms are different from mine. So your percents are always going to be different. So it lets you see the steps using your own data. Okay. Um, so I'll so I'm going to write those answers down for confidence level 1, 2, and 3. Okay. So I'll show you again what I did. So I went to data, sample. I selected my confidence levels, sample size of 3, and I hit compute. Okay. And now give me different ones. Okay. I'm going to use the first ones here. Okay. Um, right. So we're going to use confidence level 1 for M&Ms. Okay, so that's going to be all this part 1 stuff. We'll use this one for Skittles, and we'll use this one over here for sample sizes at the end. Okay. I mean, honestly, we could have used the same one for each, but we want to talk about like what happens if you change those. Okay. All right. This is on page 569. 569. Um, all right. So confidence intervals with M&Ms. Which color M&M had the lowest count in your sample? If there's a tie, just choose one. Fill out this table for that color. Okay, so I'm gonna go find my M&M data. Um, so for me, uh, I had 20. I had blue was my lowest, 21 blue. So blue, and your X value is the number of successes. So the number of, in my case, it's blue. Okay. Yeah, and so if yours was blue too, that's fine. Okay.
Hey,
If yours was a
Joe,
different color, that's right.
what if
Yeah,
you
go
have
ahead.
what if you have a low number but you have two of the same number? Because I had 11.
If there's a tie, just choose one. Yep.
Okay.
You get to pick. Which color do you want? What's your favorite? Well, it's got to be one of the tied ones. You can't just pick some random one, but uh, pick whichever of the two that you like. Oh, and Jordan, I'll show you in a second. Okay, so your X here is how many you had of that color. Okay. So in this case, it's the lowest because they wanted the lowest, but X could be, the highest or the lowest, or it could be a different one depending on what you're trying to look at. Okay. X is your successes. N is your sample size. That's your total number of M&Ms. I had 140. So that's my N. And then P hat is the probability for your sample. Okay. You'll remember probability is wanted over total. I want blues. You might want a different color, but I want blues divided by my total. So the formula is X over N. P hat is X over N. So I'm going to put that in my calculator here. For me, it was 21 over 140. And I got a nice round number, 0.15 minus 15%. Uh, if you get something a little more crazy, that's okay. So if I had gotten 20 out of 140, it would have been 0.143. So you want to round to the nearest third digit. So it says give me three digits, so I'll give you guys three digits as well. I'll do 0.150. Okay. And Jordan's question, how do I get these confidence intervals again? So you're going to click on the Chapter 9 project in Canvas. There's a link here for random confidence level. When you click that, it's going to bring you over here to this data in StatCrunch. You'll go to Data, Sample. You'll select Confidence Levels, sample size of 3, and hit Compute. And you'll write the three numbers that it picks out of the list on your paper. Okay. Awesome. All right. So now that I have that, so what I'm looking at is I am trying to figure out, okay, what is the so what percent of M&Ms are blue? Okay. My sample says that 15% of M&Ms are blue. Now, is that actually the same percent for everything in the population? No, it's not. P hat is an approximation. It's close to the true p-value of all M&Ms, okay? But it's not equal. It's close, okay? How close? That's what a confidence interval is doing. How close am I to the true population? That's what we're going to be calculating with confidence interval. We're going to find a range of data, a low, a low end and a high end, where we are 80% or 90% or 86% confident that the true value is somewhere in this range. Okay. Um, now, yeah, that sounds good, Gabby. That sounds good. Yeah, your numbers might be different from mine, and that's totally fine. And that's expected. I don't want you just copying my numbers, okay? Um, all right. So, to build a confidence interval, though, we're going to need to use the normal curve. And we know that if we have skewed data, then that's a problem. But the central limit theorem from chapter 8 says that if your sample size is big enough, then your sample distribution is going to be normal. Okay. So we can use that as long as we satisfy the requirements for the central limit theorem. So question number 3, verify all the requirements for constructing a confidence interval for the proportion of this color of M&Ms are satisfied. Okay. So what that means is we have to check and make sure that we've satisfied the central limit theorem, which has 3 requirements. It needs to be random. Your sample needs to be random, independent, and normal. We're going to be checking these 3 things throughout the rest of the class. because the central limit theorem is going to allow us to build confidence intervals. It's going to allow us to do hypothesis testing in chapter 10 and chapter 11, as long as we meet these requirements, okay? Okay. So, random. Now in class, in our worksheets, like the chapter 9 review, we said that you just have to have the word random somewhere in your story problem. Well, we don't have that here. Instead, we have to base it on our candies. So it's still a yes, though, because every M&M had equal chance of ending up in your bag, right? Equal chance of being in my bag, right? Nobody went to like the M&M store, and I don't know if they have like a big vat of M&Ms where you could pick out which ones you want. Nobody went and like picked out all the blues, right? That would not be random, okay? Uh you guys uh didn't get to pick which ones you got. You just got a bag from, from Kroger or Meijer or whatever, and whatever was in there, that's what it was, right? So that is random, okay? Mhm. Um, Independent, we need to make sure our sample size is not too big. So we need to make sure that 20n is less than our capital N, our population. So for me, my N was 140. So I need to do 20 times 140. And I get 2,800. All right. So is that less than my population? My population is all M&Ms. So are there more than 2,800 M&Ms in the world? Yeah, there's way more than that, right? This is definitely a yes. Okay. Trillion. There's trillions of M&Ms. Yeah. So hopefully nobody went out and bought 5% of the world's M&Ms. In your case, you would have a no. Okay. So I don't think anybody did that. Um, that would be very newsworthy. All right. Uh, Next is normal, and this is where your sample might break down. Independent, your sample can't be too big. For normal, your sample can't be too small. Oh, Corbin did. Your sample can't be too small. So we need to check NPQ is bigger than 10. Okay. Now, if we were looking at means, right, there's a central limit theorem for proportions and a central limit theorem for means. And you need to know which one you're doing. They're very similar. Okay. One difference is the normal part, right? If we were looking at means, like if I wanted to see like how much the average M&M weighs, I would weigh them all, I would get a number, and I could average those, right? That's not what I'm looking at. I'm looking at M&M colors, and color is a qualitative variable. So I'm going to be looking at proportions in this case. So for means, you need to make sure that n is bigger than 30. For proportions, because I'm asking like what percent of M&Ms are blue, I need to check n times p times q has to be greater than 10. So my n is 140. My p, now I wrote p here, but we don't know p actually. So technically I should have written p hat and q hat. It doesn't matter. You're never going to have both p and p hat, okay? Um, so in this case I meant p hat. It's 0.15. Okay. I need my q, which is 1 minus 150. So my Q is 0.850. Okay. And I need to multiply those together and see what I get. So for me, 140 times 150 times 850. Mine is 17.85. And that is bigger than 10. So mine is a yes. Okay, so I got three yeses. Yes, yes, yes. So that means that my confidence interval is going to be accurate. It's going to be reliable. Now, you might not have gotten three yeses. Oh, and right, yeah, you can how many decimal places? It didn't say how many decimal places. So yeah, you can do two decimal places. That's fine. Um, so I got three yeses, but you might not have. Is there anyone on the call that did not get three yeses? So Jordan didn't get three yeses, neither did Nicole. We have a couple different people who did not get three yeses. So I'm gonna hope that you got a yes here for the first two. I said three yeses. I didn't actually specify which one is not a yes. So hopefully nobody went and like picked out non-random ones. And also hopefully nobody bought, trillions of M&Ms. So uh most people, if you're getting a no, it's because your sample is too small. And that's one of the most common things that happens in the real world is people don't take a big enough sample. Okay, so you have to redo it. Okay, Isaiah got 13. Yeah, that's bigger than 10. So yours is a yes. Okay, so if you did get a yes, I'd love to know what was your sample size and what was your p hat. If you want to drop those in the chat for me. Gabby, you were so close to 10. You got 9.8, but that's still a no. Which is fine. If you got a no, that's no big deal. So Isaiah's was 165, which is actually more than what I had, but your p hat was really small. Um, so James had, oh, you had a really big sample size. So usually, um, a usually a sample size that's too small is what causes no's. Okay. Mike, I think yours is a yes. Mike's got a p-value of 0.152 and 554. Mike, I think 554 times 0.152 times your Q value, which would be 0.848. I think, yeah, yours is 71. Yours is yes. Um, I guess, yeah, so yeah, yours is yes, so there. But I was curious for the people that got to know how big your sample sizes were. Um so Rachel's was 92, so that's smaller than what I had. Yeah. Gabby's was 105. That's smaller. 76 is that one's smaller. So 108. Yeah. So um if we ran our numbers and we get a result where it's not bigger than 10, that means our confidence interval that we're building is not going to be reliable. It's not going to be accurate. Okay. Now, that doesn't mean I need you to go buy more M&Ms. Okay. In the real world, it would. We wouldn't be able to use these numbers. We'd have to go back and get a new sample. Okay. Nicole only had three red ones out of her 108. So not only did she have a small sample size, she also had a small p hat value. So yeah, that's crazy. Because even if you do have a large sample size, if your p value is very small, then that's still going to be a problem, right? Because I had mentioned like if you are a advertising executive and you want to see how effective your commercial is, if you have a sample size of 1,000 people, well, a good commercial uh, success rate is like 0.5%. So like if I multiply that times 0.005 and then times my Q value, which would be like 995, that means I'm only going to have four people that see my commercial, four or five people that see my commercial and make a purchase. That's not enough. I am going to need a much bigger sample size in that case. Okay. So anyway, let's move on to the next page though. page 570. So regardless of whether or not you got yeses or nos, okay, we're gonna keep going and see what happens, okay? Um, construct a confidence interval for the proportion of of M&Ms that are your color. So mine were blue. Using confidence level number one. So are you going to be using this confidence level for M&Ms? So I want to build a 86% confidence level, confidence interval. Anyway, we need to show the formula. We need to show the substitution. And we need to show the result. Okay. Um, okay, so the formula is going to be on page 259 in our exam notes packet. On page 259, we have the confidence interval formula for single proportions and confidence intervals for single population means. Okay. So it's important to know whether I'm looking at means or proportions. They are similar, okay, but they're not exactly the same. Okay. Uh, for today, since we're looking at proportions, we're going to be using this formula. Okay. Now this is the formula I'm going to write down, and it looks crazy complicated. Okay, but it's not. It's looking at your point estimate, which is p hat. So my question is, what percent of M&Ms are blue? My sample says 15% of M&Ms are blue. Okay, that's going to be the center of my confidence interval. Now, are 15% of M&Ms blue? No, it's not. It's close though. We actually do know the answer. Normally, we don't know what the population true proportion is. Okay, like if I ask what percent of people in the US have red hair, we don't know that. What percent of people are going to buy after they see my commercial? I don't know that unless I do a sample, okay? Uh, what percent of people are going to be, or what percent of the time is my vaccine going to be effective? What percent of the time is my vaccine going to, save people, right? I can't know that for the entire population, okay? But we do know the answer here for M&Ms because M&Ms make equal numbers for all of their colors. There are 6 colors. So 1/6 in your calculator is 16%, 0.16666. So my guess was 15%, which is not correct. It's actually 16%. Those are very close. Okay. So that's the idea with a confidence interval is what range would the true value be based on this? So you have your p hat, okay? And then you're going to calculate a low end and a high end for your range. So you add and subtract your error, okay? So in my case, like 15%, that's not true. It's off by a little bit, right? I have an error of some number, right? And I'm hoping that my error is small enough that the true value is going to land somewhere in that range, okay? So the calculation for the error is this crazy thing, which still looks complicated, but it's not. It's just z alpha over 2, which we've talked about in chapter 7, times the standard error, okay, which we've also talked about in chapter 8, okay? So anyway, this is the formula I'm going to write down on page 570. So p hat plus or minus z alpha over 2 big square root p hat q hat over n. That's my formula, okay? Substitution, I'm going to replace all the letters with numbers. So my p hat was 0.150, okay? Yours is different, which is fine. Okay. Plus or minus. I'm going to leave Z alpha over 2 blank for the moment. Come back to it. My P hat was 0.150. My Q hat was 0.850. And my N was 140. Okay. All right. There's two ways that you can calculate your confidence interval. One is using a pair of calculators, and the other is using StatCrunch. I'm going to show you both, okay? First, I'm going to show you with two calculators. Now, I need a calculator for Z alpha over 2. To get that, what we did in chapter 7 was we went to stat calculators normal. Stat calculators normal, okay? And we want to select between. Confidence intervals are always going to be between. We want the low end and the high end, okay? We want to say our true M&M blue percentage is somewhere in this range, okay? So it's always going to be between. And I'm going to put in my confidence level. Mine was 86.3%. That was my confidence level for number 1. Yours will be different. Whatever it is, you're going to put that in there, okay? And you hit compute, and it's going to show you your Z value. My Z alpha over 2 is 1.4871, okay? So that was stat, calculators, normal, selected between, put in my confidence level, hit compute. And I'm going to write that right here for my Z
Hey
alpha
Joe,
one.
mine's won't compute, and my mean is 0, standard deviation 1, and then I put my confidence level, which is 97.3.
Did you write 97.3 or 0.973?
No, I wrote 97.3.
No, no, no. So that's a percent. So um, whenever you have percents, um, if you write the percent symbol on your paper, I will accept that. This confidence level is not 86.8. It is 86.8%, which is 0.863 as a decimal. Or sorry, 8. Did I write? Did I put the wrong thing in?
Wait,
Yeah, I put the wrong thing in, didn't I? Yeah, whatever. Okay. So
okay,
you need to put it in as a decimal. Okay.
so mine would be 0.973.
Yes.
Okay, thank you.
Yep. This number here is a if you hover over it, it says it has to be a number between 0 and 1. So if you put in 97, well, that's bigger than 1, so that will not work. So always has to be between 0 and 1, and then you'll be good. Okay. Now, you don't have to do it this way. I'm going to show you two ways to do it. So if it wasn't working for you, that's totally fine. I'm going to show you a different way to do it in a second. Okay. But I'm going to keep going with my calculator method first. So I plugged in my numbers. I used my calculator to get this, and now I'm going to use Desmos, which is the other calculator that we're going to use to calculate our result. So I'm going to come over here to my calculator, and I'm going to type all of this stuff in, 0.150. Start with the minus. Do the minus first, and then times SQRT 0.150 times 0.850 divided by 140. Okay. And my result is 0.1045. Okay. Uh, and obviously your result will be different from mine, but you'll write that as the first part. That's the lower limit of our confidence interval. To calculate the upper limit, I need to do the plus. So I don't need to type the whole thing back out again. I just need to scroll over here and change my minus to a plus. And now I have 0.195. Okay. And so That's my lower limit, and that's my upper limit. Okay. So it looks complicated, but when you type it in the calculator, it doesn't take that long. Where did my 1.5063 come from? I screwed up and put the wrong percent in here. I put in 0.863, so I changed it. Now it's 0.868. Anyway, and then recomputed it. So it is the Z value. It's Z alpha over 2. That's my Z value. Obviously, yours will be different because you have a different confidence interval. So, Gabby, she said a second ago, hers was 97.3, 97.3% as a decimal 0.973. Her Z value is 2.2115. And that's what she would put right here for her Z alpha. Okay. This is my confidence interval. What does it mean? So my earlier question was, what percent of M&Ms are blue? Well, I can't calculate that for the population. So I took a sample of 140 M&Ms and I got that 15% are blue. Now, my sample says 15% are blue. I know that that's not completely accurate because this was a random sample. Maybe I got a little less blue, maybe got a little more blue. So what range do I think the true answer to the question is? Okay. What percent of M&Ms are blue? Well, I am 86% confident. 86.8%. I am 86% confident that the true answer to the question, what percent of M&Ms are blue, is somewhere in this range, somewhere between 10% and 19%. Okay. Now, that does mean there's still a chance that I'm wrong. There's still a 14% chance that the true value is outside this range. Okay. But I'm 86% confident in this. Okay. If I wanted, I could have said, oh, well, I need to be more confident. I want to be 95% or 99% confident. Okay. So now, this is what I got for calculating using the calculators, okay? This is not the only way I could have done it, so I'm going to show you a different way. Using StatCrunch, you would do stat, proportion stats, one sample with summary. Stat, proportion stats, one sample with summary. I'm going to show you how to do that as well. I've already got the answer here, but I'm going to do it again and see what I would have gotten with that. I'm going to close this guy. Stat, proportion stats, one sample with summary. Number of successes is your X. In my case, I had 21 blues. Number of observations is your sample size. I had 140. We're going to do hypothesis testing in chapter 10. I don't want to do that right now. You're going to click this blue button down here for confidence intervals. Confidence intervals is what we're focused on right now. And I need to put in my confidence level. Mine was 86.8%. And then you want to check this box right here, show critical value. That'll give you your Z. Okay. And I'm going to hit compute. It gives me this. Okay. So I'll show you that again. Stat, proportion stats, one sample with summary. Put in your X value. Put in your N value. Select your blue dot right here for confidence interval. Change it to whatever confidence level you want to look at. And then select this button for the Z value, and then you hit compute. Okay. And this is what I get. I get a Z value of 1.5062. And you notice my Z value that I got earlier is 1.5063. They're off by a tiny little bit, and that's because of rounding. Okay. So these two ways of getting it are going to be close. They're not going to be the same. Rachel said that her calculation for StatCrunch and her calculation for Desmos are not matching up. Okay. And that's because of rounding. Okay. So I'm okay with that. Whichever answer you put in will be fine. Technically, StatCrunch is going to be the one that's more accurate just because they don't do the rounding until the end. It's fine. It's no big deal. Okay. So here's my Z value. Oh, I think actually it is 0.5063. And here's my lower limit, which I'm going to write as 0.1045, and my upper limit 0.1955. Okay. So so there's my StatCrunch and Desmos matched, yours might not. Okay. That's okay. That's not a big deal. Whichever way you like better is fine. Okay. Uh, I'll show you when we do Skittles. I'll do it the other way around. I'll do that one first. Let's keep moving on and see what happens with our confidence interval. So, question number 5. Willy Wonka claims that the proportion of candies of my color blue is less than 1/6. So, um, eh, Jordan, you can write down either one. You don't need to do both. Okay. So Willy Wonka claims that the proportion of blue candies is less than 1/6. Does your confidence interval support his claim? So he comes to me and he's like, there's something shady going on at the M&M company. Like maybe blue dye is more expensive and they're not producing the same number of blues as every other color. Okay. That's what he's telling me. Does my result support his claim? Well, you don't need to draw a number line, but it helps me visualize it. Okay. So here's my x-axis or your number line or whatever, right? I am 86% confident that the true percent of blue M&Ms is somewhere in this range. Okay. 0.15, that is my p hat. That's dead in the middle. This is my error and this is my error. So if I add my error or subtract my error, I get my lower limit and my upper limit. Okay. So I'm 86% confident that the true value is somewhere in this range. He says that 1/6 is not, that they're not producing 1/6. Okay. Well, where does 1/6 land? 1/6 as a decimal is 0.1667, which for me lands right here. So for me, that number is inside my confidence interval. So in that case, he's claiming that there's something, he's claiming that they're making less than a 6. And I do have some numbers in my confidence interval that are less than a 6, but I also have some that are more than a 6. And so I do not support his claim because 1/6 is inside of my confidence interval. It's between my upper and lower limit. Now, for you, maybe you didn't get this. Maybe you got 0.14. For that case, where would 0.166666 be? That would be way up here. Okay. So for that case, um, he's claiming that the true value is less than 1/6. Well, you don't know what the true value is. You know it's somewhere in this range, but all of these numbers in this range are less than 1/6. So in that case, you would say, oh, I support that because my entire interval is below 1/6. Okay. Um, so depending on where 1/6 lands, if 1/6 is in your interval, you would choose this one. If not, you would choose this one. Okay. So don't circle both of them. Okay. Um, you want to circle just the one that's is for your confidence interval. Okay. So yeah, so for you guys, I'm curious, did anybody get support or not support? What did you get? Support or not support? I got some supports. I got a not support. Got a support. Yeah, so Mike had 500 in his sample size. He had a huge bag. So his data is going to be super accurate. So that means that his confidence interval is going to be very near 1/6. So, um, yeah. Okay, so moving on. Um, let's look at question number 6. Suppose you had a super big bag with thousands of M&Ms in it. Okay, so still bigger than yours, Mike. You had 500, but if we had 1,000 M&Ms, we'd be counting for a long time. But if we did that and we still got the same proportion as we did in question number 2, okay, so if you still got the same p hat, mine was 15%. You got the same value, what would happen to your confidence interval? Confidence interval created using the numbers from this bag, will it be narrower or wider? Um, so let's start with that. Narrower or wider? Give me a guess if you think it's narrower or wider. If your sample size was huge, so uh, I've got some wider, got some narrower. Um, so there's a table that Sydney and Elaine can go over with you that talk about the relationship between confidence intervals and sample sizes and things like that. But there's an axiom that I'm going to keep referring to over and over. If you have a larger sample size, that means more accuracy. Okay. So what does that mean? If we have a large sample size with thousands of M&Ms, our result is going to be more accurate. Well, what does that mean for our confidence interval? You'll remember that the confidence interval is telling you uh, where you think the true value of what percent of blues M&Ms there are is going to land. My confidence interval is very wide. My confidence interval goes from 10% to 19%. That's a 9% distance. Half of that is 4.5. That means I have a margin of error of 4.5 this way and 4.5 this way. 4% this way, 4% this way. That's a pretty big margin of error. Okay. And it's because my sample size is so small that my error is so big. If you have a large sample size, your error will be smaller, and that will mean that you end up with a confidence interval that is narrower. Okay, so your confidence interval will be narrower because sample size and error have an inverse relationship. Okay, I'll show you. I can show you with the numbers. If I come back over here to my calculator, okay, if I change my sample size from 0 point, or sorry, if I change my sample size from 140, and if I change that to say 2000, now my upper limit is very close to 16%, and my lower limit is very close to 14%. So instead of looking from 10 to 19, which is really wide, I'm only going to get a sample size, or sorry, a confidence interval between 14% and 16%. So that is much narrower. Okay. And it's because sample size is in the denominator. If you divide by a large number, dividing by a large number means your result is very small. Think about it like this. 1 divided by 100 or 1 divided by 2. Which of these is bigger? 1 over 100 or 1 over 2? Which of these is bigger? 1 over 100 or 1 over 2? 1/2 is bigger than 1 over 100. A half dollar, 50 cents, is definitely worth more than a penny. But that doesn't make any sense but the number 100 is definitely bigger than 2. Yes? When you have a large number in your denominator, it means your result, your fraction, is very small. So putting a large number in your sample size means you have a small error. Okay. So everybody should be choosing this one. So for question number 5, you would select support or not support depending on where 1/6 lands in your confidence interval. So some of you picked this one, some of you picked this one. But for number 6, everybody should be picking narrower. Should be picking that one. Okay. So no, Gabby, you should be picking the same as me, narrower. Okay. If your sample size had been bigger, you would have had a more accurate confidence interval, which means it would have been narrower. Okay. Let's move on to Skittles. Page 571, we're going to talk about Skittles now. But the steps are going to be very similar. Okay, so practice, rinse, repeat. Which Skittle color had the highest now? So this time we're going to switch to highest count. Still, if there's a tie, just choose one. Let's see what I had. For me, I had the most green. X is your success rate, so you're going to write the number for, in my case, I had green. I had 54 green. In fact, did you have the same as me for both Skittles and M&Ms? Someone said they had blue as well, which is fine. Yeah. So Yvette and I are on the same page. At least our samples are anyway.
Wait, Joe,
Um,
I,
yes.
I thought X was the one we had the lowest count. Is it it's highest count? Okay, I read that. Okay. I read that wrong.
No, we want to do highest count this time. So for Skittles, we're doing highest, and your sample size is total number of Skittles you had. So mine was 238. P hat is X over N. Oh, Gabby is yellow and yellow. Interesting. Um, I know what your answer is going to be for chapter 11 then. It's going to be yellow. Okay. Uh, yep, that sounds good. Um, oh, Yvette's I had 238. Yvette had 239. We're in sync. All right. P hat. What's my P hat? 54 divided by 238. My p hat in this case is 0.227. Okay, 0.227. That's mine. You might have something different. Verify whether all requirements for constructing a confidence interval for the proportion of this color minus green are satisfied. We want to show that our sample was random. It was independent. And we want to show that it's normal. Okay. So random, yes, each candy or Skittle had equal chance of being in my sample, right? So for M&Ms, like if they had a huge bin of M&Ms, I don't know why you would just pick out all the blues. They'll taste the same. But for Skittles, like I would definitely go and like not pick any of the yellow ones. So, but hopefully nobody did that. So you just bought a random bag at you know at the store at Target or whatever, and yeah, you're good. Independent. I need to show 20 N is less than population. So in my case, 22 times 238 is less than N. 20 times 238 is 4,760. And that is definitely less than the number of Skittles. Right? Definitely a yes. And finally, for normal, we need to check that NPQ is bigger than 10. So my N is 238 for Skittles. My P hat is 0.227. I need my Q. 1 minus 0.227 is 0.773. So I need to multiply N times P times Q, see what I get. Okay. 238 times 0.227 times 0.773. Mine is 41.8, and that is definitely bigger than 10. So I am good. Okay. All right. 3 yeses. That means we're good. Now, I've said before that, like, honestly, like a sample size of like 140, even that is probably too low for a sample size. We've seen already there were a couple people that had sample sizes for M&Ms that were like 70 M&Ms or 100 or whatever, and they ended up getting a no here. Because 17, my number is bigger than 10, so I did get a yes, but even that is still too small. I would have very much preferred a sample size like in the 200s, 300s, or even a sample size of 1,000. Okay. So sounds good, Gavin. Yeah. Most people will probably get a yes on this one. 700, Mike got 752. Nice. Mike wins the most accurate. Yeah. I keep saying larger sample size is more accurate. If Mike's numbers end up not being accurate, because it is random, it is a random sample. I'm gonna have to eat my words. So Um, question number 9. Regardless of whether you got 3 S's or not, construct a confidence interval for the proportion of Skittles. So we're going to make sure we're going to do our formula. We're going to do our substitution and then our result. Okay. The formula for this is the same formula that we had before. So page 259, we're just going to copy that down. So P hat plus or minus Zalpha over 2 square root E hat Q hat over N. There we go. Then we'll substitute in our Skittle numbers. So my Skittle numbers, my P hat was 0.227. I'm going to leave space for my Z alpha over 2. I'm going to leave that out for now. P hat 0.227. Q hat was 0.773. My N was 238. Okay. Right. So there's 2 ways that you can calculate your confidence interval. One is using a pair of calculators. You can use the StatCrunch calculator, Stat calculator's normal to get this one, and then a decimals calculator. That works fine. This time I'm going to use StatCrunch. I'm going to do it this way. I'm going to do stat proportion stats one sample with summary. Stat. I'm going to close this so I don't confuse myself with all this other stuff I got open because that was M&M's. Stat, proportion stats, one sample with summary. Number of successes, that's my X. I had 54 green. I had 238 Skittles altogether. I'm going to click the blue button here for confidence intervals. And this time, I'm going to switch my confidence level. So we we were doing this one, this confidence level for M&Ms. Now I want to use this confidence interval. So I want my confidence interval, they want us to use the confidence level from number two. Okay, so I'm going to use 75.8%, which as a decimal is 0.758. Okay, click this button here so you can get your Z, and we'll hit compute. And here's what I got. So I'm going to write down my Z value, write down my upper limit,
I'm
my lower limit.
sorry, Joe. How did you get to that again?
Yep. So I did stat, proportion stats, one sample with summary. That's on page 259. Okay. Stat, proportion stat, one sample with summary. And then I put in my X. In my case, I had 54 greens. I had a total of 238 Skittles. That's my N. That's my sample size. Click this blue button for confidence intervals, and you're going to put in your confidence level number 2, and then you're going to click this button right here for critical values. Okay. Once you've done that, you hit compute, and we get this, and I'm going to write my answers down here. So my Z value is 1.1700. Okay, that's my confidence or my Z value. Yours will be different because you had a different confidence level number 2, right? For Skittles, okay? And then our result, we write the lower limit, 0.1951, comma, our upper limit, 0.2587. Okay? And we're good. Um, And again, if you didn't want to do it that way, if you felt more comfortable using a pair of calculators, so you could use the stat calculators normal to get your Zalpha over 2, and then use Desmos, just type all that fun stuff in. You can do it either way. I don't mind. Okay. Um, yeah, so normal rounding rules apply. So you will round it. So I think what I had was it said 0.2586, but I need to round that 6 up because the 5 next to it rounds it up. So I wrote 7. Okay. All right. Um, so uh so the question I'm trying to answer is what percent of Skittles are green? Okay. And I can't calculate that for everything. I have to do a sample. And so I got that 22% of Skittles are green. Is that true for the entire population? No, it's not. Um, that's close to the true value. How close? Well, I am 75% confident that the true green percentage is somewhere in this range. Okay, that means there's a 25% chance that I'm wrong and that the green value, the true proportion is outside that range. Now, what is now the true proportion? We actually know the answer here. Skittles has 5 colors. They make all the same, uh, they make the same number of each. So 1/5 in your calculator, 1 divided by 5 is 20%. Right? So I'm close to 20%. I'm not, dead on, but I'm close enough. Willy Wonka is bothering you again, and he claims that the proportion of candies of your chosen color is more than 20%. So, in other words, he's claiming that, there's something weird going on at the Skittles company, and they're actually making not the same amount of greens, they're making more greens than all the other colors. And so we're going to check and see if that's true. Now, why do we care? Like, uh, if he came and told me that more than 20% of eminent of Skittles are yellow, I'd be like, oh, I'd be up in arms, right? I don't like the yellow ones. Um, so we're going to check where 20% lands in our confidence interval. So my confidence interval goes from 19% up to 25%, right? So here's my confidence interval. I am 75% sure that it's somewhere in this range, okay? 20% for me is right here. It's just barely inside my confidence interval. So I do not support his claim because 20% is within my interval. Oh, Mike's giant sample size actually ended up uh being this one. So um if 20% is not inside your sample, you would say support because the entire interval is above 20%. So don't circle both of these. Your answer is one of them, depending on where 20% lands, whether it lands inside or outside your confidence interval. Okay. Um, Mike, so your even though you ended up supporting his claim, oh, and it's yellow. He has a giant bag of 700 Skittles. Most of them are yellow. Yeah. So Mike, your confidence interval is much smaller than mine. Mine goes from 19 to 25. That's a difference of six. Um, yours goes from 20 to 23, which is only a difference of three. So your confidence interval is much narrower than mine, which means it is still more accurate. But I'm curious what your confidence level was. What was your confidence level?
1.11.
Oh, that's your Z value. What was
Oh,
the
sorry.
confidence level you
Uh,
had for number two?
uh, sorry. Number two was 73.3%.
Oh, so yeah, so your confidence level is pretty small. So you're 73% confident that the true
Yeah.
value is somewhere in that range. If you had used a higher confidence interval, like if you're like, I want to be 90% confident, then we'd have been good.
And
So
yellow
that
was my
means
highest one.
yeah, yellow was your highest one, yeah. So if if you are only 73% confident, that means that there's a 27% chance that the true value of yellows is outside your range. Okay. For me, I was looking at a 75% confidence level, which means there's a 25% chance that I fall somewhere outside of that. So that's what the alpha is. So, um, your confidence level and alpha are closely related. So, for confidence intervals, we are always using between, okay? And the red part is your confidence level. It's how confident you are. I want to be 90% confident or 95 or 99%, okay? Um, but there's always going to be some error, which is what your alpha is here, which is the white spaces. So, um, if you have 75% of your uh, curve is red, that means the 25% is your alpha. That's the white space here. Okay. And we write it as Z alpha over two because there's two alpha sides. We basically take that, that error rate, that 25% I said a second ago, and you cut it in half and you put some out white on this side, some on this side. So anyway. Um, all right. Well, moving on. So suppose when creating the confidence level for number nine above, instead of using the confidence level from number two, if you had instead used confidence level one, what would have happened? Okay. So you're going to look at your number two and your number one, you're going to compare them. So, for me, my Skittle one was 75%. If I had instead used a confidence level of 86%, my what would have happened? Would my confidence interval have been narrower or wider? Okay. So if I'd wanted a larger confidence level, it means I would have had a larger confidence interval. Okay. So mine would have been wider because confidence level and error have a direct relationship. Okay. So basically, you're going to look at these and say, all right, if this one is small and number one was big, then you would have had a wider confidence interval using that bigger number. If it's the other way around, if number one is small and number two is large, then you would have had a narrower confidence level. So your answer is going to be one of these, depending on whether number two is bigger or number one is bigger. Okay. Think about it like this. If I'm a basketball player and I want to make 99% of my shots, well, then I could make a giant hoop. If my hoop is huge, like a swimming pool sized basket, I'm going to make 99% of my shots. No problem. Okay. On the other hand, if I only want to make 10% of my shots, then I would be okay with a tiny little hoop. Okay. Where I'm not going to make it very often. So, if your confidence level is large, that means you'll have a wide confidence interval. Okay. And that's what happened, Mike. You randomly picked a 70% confidence level, which meant your confidence interval was really small. And so it just barely missed the 20%. That's fine. Okay.
So you're safe with the yellows, then there's a larger chance that I'm wrong.
Nice. All right. Page 573. So this is the last page for the project tonight. We're going to look at sample sizes. So yeah. Yep, you got it, Kevin. Okay, so I said earlier that if you have a large sample size, then your results will be more accurate. And we saw earlier that there were some people that ended up getting a no for normal, and that meant that their sample size was not big enough. Okay. And if that was the case in the real world, if we were doing a test, like we were testing to see how effective our medicine was, and we see that our sample size is not big enough, okay, we would need to go get another sample. We would need to go get some more people to test. Okay. How many more people? That's what we're going to look at next. Okay. So let's say that, so another reason we might want to do this is, my confidence interval for M&Ms was from 10% to 19%. That's a huge range, right? That's a 9% range. Okay. So, I'm 86% confident that the true value is somewhere in this range. Well, it could be 11, it could be 12, it could be 13. That's a pretty large range. And so I want to be more accurate. That means I need a larger sample size. How big of a sample size? Let's look at number 12. Calculate the minimum bag size, as in the number of candies you would need to sample, required to ensure that the proportion of your color of M&Ms is within 2% of the true population proportion for that color. Use confidence level 3 and assume you do not have a prior estimate for the proportion. So confidence level 1 was for M&Ms, 2 was for Skittles. Number 3 is what you're going to use for sample sizes. So I'm going to be using 70.8% for my confidence level for this page. Okay. So I want to be 70% confident that the true value is within 2% of my of the true population. So in other words, I don't want to be looking at a 9% range. Okay. I want to say that my error is +2% +2 or -2. Okay. So I would be okay if it's like from, you know, from like 13 to 17. Okay. So I want a narrower confidence interval. So to do that, I need to show my formula. I need to show my substitution and my results. Okay. All right. The formula for this is on page 261. Okay. Page 261 is population sample size for sample size for population proportion or sample size for population mean. So it's slightly different depending on whether you're doing proportions or means. So again, pay attention to that. Okay. We're doing proportions, and there's two of them. There's if you have a prior estimate or no prior estimate. They said pretend you do not have a prior estimate, so I'm going to be writing this formula. So my formula is n equals 0.25 big parenthesis alpha over 2 error squared. Okay, that's my formula. Substitution. There's only two numbers to substitute in. I need my z alpha over 2 and my error. My error, I want my error to be within 2%. So 0.02. Okay. So everybody's going to have the same error for that. Okay. But my z alpha over 2 is going to be based on your confidence level. Mine's 70.8, which is pretty small. So I'm going to get a really small z value. That's fine. To do that, I need the normal calculator. So it is stat calculator is normal. We do between. Everything for confidence intervals is between. And you're going to put in your confidence level from number 3 minus 70.3%, or no, 70.8. And my z value is 1.0537. So once again, that was stat calculators, normal, between, put your confidence level in there as a decimal and hit compute. And you're going to write your z value here. Okay. Same stuff that we did in chapter 7, right? When we were looking at what percents go with what z values. Okay. All right. Now that I've got that, we just type this into the calculator and see what we get. 0.25 times big parentheses 1.0537 divided by 2% as a decimal is 0.02. Close your parenthesis by hitting the right arrow key and then close your parenthesis. To square this, you hold the shift button and hit 6. Shift 6 is up arrow, and then you hit 2 and that will square it for you. And I get 693.92. Okay. And that is not the answer. Okay. Because I can't sample 693.92 M&Ms. 0.92, what does that mean? Like someone took a small bite out of it and I keep the other 9.92 of it? No. When I'm sampling, I always am looking at whole numbers. It doesn't matter what you're sampling, people, sampling, cars. If you're, that's how car companies test their cars for safety. You can't go and crash every car. That's the population, right? The population is all cars that you're making. So if you want to say that we have a safety rating of 99%, to do that, you have to take a sample of your cars and crash them. And so you can't take 0.92 of a car. You have do a whole number. Okay. So when we are doing sample sizes, we will always round up. Okay. So normal rounding rules apply for everything in the class except percentiles where you round down and sample sizes where you round up. Okay, so we round up and it would be 694 M&Ms. Now, we would have rounded this up anyway because 0.92, does round up. But if this had been 0.12, I would still round it up to 694. Because if you round it down, you're not going to have a 2% margin of error. You're going to have a 2.1%. And that's not what we want. I want to be within 2. So if you round it down, or sorry, if you round it down, that's going to go the wrong way. If you round it up, well, now you're looking at like a 1.9% margin of error, and it's within 2. So that's good. That's fine. Okay. So you want to round that up. So Gabby, for yours, you want to round it to the nearest whole number that is bigger than that. Okay, so yours would be 1,579. All right, suppose when you were completing number 14, you had used a 1% margin of error instead of a 2%. Your sample size would have been bigger, smaller, the same, larger. What do you guys think? Smaller, the same, or larger? You got a 1 in 3 shot. It's not test day. Take a guess, right? Yvette says larger. Mike says larger. Yeah, you guys got it. It is larger. Why is it larger? You'll remember that a larger sample size means you will be more accurate. So instead of having a 2% error, a 1% error is more accurate. Okay. If you want to see it, I can show you. So if we had instead of doing 0.2, if we instead of a 2%, if it had been 1%, now instead of sampling 600 M&Ms, I'm sampling 2,000 M&Ms. So it's much larger. Okay. Okay. Perfect. Calculate the minimum bag size again with the same confidence level and the same error rate as in number 14, but this time use your p hat from number 1 as a prior estimate. So for question number 12, they said, all right, we want to redo this experiment with a larger sample size so that we can be more accurate. We want to be within 2% of the true population. Okay. So how many M&Ms do we need to buy? Okay. And we had no prior estimate. Well, that's not true. We did have a prior estimate. We already did the experiment. We already did all the counting and stuff. And our previous estimate was whatever p hat was from number 2. So my p hat was 0.15. Okay. So I can use that to help me figure out how many I need to buy to redo the experiment. Okay. So I didn't need to do this for number 12. That was a waste of time. Because I had a prior estimate. So with a prior estimate, it's this formula. It's the same formula, except instead of 0.25, you have p hat q hat. Okay. So formula, substitution, and a result. So now it's p hat q hat is alpha over 2 error squared. Okay. And our substitution, my p hat for M&Ms. Make sure you're doing the M&M one, not the Skidoo one. My p hat for M&Ms was this. My q for M&Ms was this. Your z value is still the same. from number 12. They want you to use the same confidence and the same error. So you don't need to change that part. So my Z value was 1.05. It's still 1.05. My error rate is still 0.02. Square that. Okay. So now I'm going to go back over to my calculator and we do 0.150 times 0.85850 parenthesis 1.537 divided by 0.02. Push my right arrow key, close my parentheses, shift 6, square that, and I screwed something up. What did I do wrong? Oh, no, no. I did. I did. Mail, Cindy, what did I do wrong? When you have a prior estimate, it should be smaller. Ah, thank you. There it is. Rachel got it. Ah, there we go. That's
She
better.
got it before me.
What's that? Yeah. Um, when you have a prior estimate, your sample size should be small. So I had my critical value wrong. Okay, right, I had it. My N is, oh, I closed it already. 353.9, which I need to round that up, and it'll be 354. So if you have no clue, so like if I wanted to see if I wanted to know what percent of people in the US have red hair, does anyone have a guess? I have no clue. Uh, is it 10%? Is it 25? It can't be 25%. That's ridiculous. 5%? I don't know, right? We have no clue. Mike's gonna guess 5. When you have no clue, you have to do it with no prior estimate. Now, if you've run the experiment once and you have an estimate and you want to run it again, your sample size will be smaller if you have a prior estimate. So that's why you would want to use this formula. This formula is better, right? Think about like if I have to go and buy 694 M&Ms, I mean that's fine. It's just going to take me a long time to count them. It'd be better if I only had to buy 354. Okay. And M&Ms like are good because you can still eat them and enjoy them. Like imagine if instead we had to go and Mike said it's a long time to count. Imagine instead if we were looking at like how effective our COVID vaccine is. Okay. If I have no prior estimate, I'm gonna have to inject my vaccine into, 1,000 people, which means I have to get 1,000 people. I have to pay my technicians. I have to have 1,000 vials of the vaccine, so it's going to take longer to produce, right? It's much easier if you have a smaller sample size. So if someone else has run their vaccine, their experiment previously, then it's better and easier if you have a prior estimate because you have a smaller sample size. Okay. All right. Lastly, of the 3 confidence levels, which would yield the largest sample size? Um, yeah, so yes, Gabby, you're going to use the same confidence as level 3, as number 3. Yes. So here's my 3 confidence intervals, right? I had 86 and 75 and 70. Okay. Which one would yield the largest sample size? Um, so if you want to be more confident, you want to be more accurate, you need a larger sample size. So you're going to circle whichever of these is largest. For me, number one was largest. So if I want to be super accurate, super confident, I'm going to need a big sample size. So my sample size was actually pretty small for this one, 694. You guys probably ended up getting sample sizes in the thousands, right? And this one was only 300. That's less than Mike. You guys probably had something a lot higher than what I had because my confidence level for number three was tiny. So, um, that is it for tonight. So if anyone has any questions, feel free to stick around. I did record the entire session, both the morning and the evening. So if you want to watch that, you can.